Hello everyone, myself Dr. Subhendu Sarkar. I am an assistant professor in the Department of Chemistry of Brennward University. Today we are going to talk about a very important and fundamental concept in chemistry, which is Nernst equation and its various applications. So let's begin. So this equation was introduced by the German chemist Walter Hermann Nernst. So what is this equation is all about? This equation provides a relation between the cell potential of an electrochemical cell and the standard cell potential, temperature, and the reaction quotient, that is the concentration of the reactant and the product. So this equation we oftenly use to calculate the cell potential of an electrochemical cell at any given temperature, pressure, and reactant concentration. So, what is the Nernst equation? So, let us consider reversible chemical reactions where capital A, B, and C are the reactants, and with a stoichiometric coefficient designated as small a, small b, or small c, and capital X, capital Y, capital Z are the product one with stoichiometric coefficient designated as small x, small y, small z. So Nernst equation says that the cell potential of this uh, reversible reaction E cell will be E0 cell, that is the standard cell potential of the cell, minus RT by NF ln concentration of the products divided by concentration of the reactant. So this is popularly known as the reaction quotient. So here R is the universal gas constant, T is the temperature in the Kelvin scale, N is the number of electron change during this chemical reaction, and F is the Faraday's constant. Now if we put the values of R and F and we assume that the temperature in Kelvin scale to be 298 Kelvin and convert ln to log, we will get E cell equal to E0 cell minus 0.05912 divided by n log of concentration of the product quantities and the concentration of the reactant quantity. So this is the simplified form of Nernst equation which we actually use for various calculation. So for a half cell reaction, let's say we are considering the half cell reaction. So we are considering an oxidized state of a species, and we are putting n number of electrons with the species, and we are getting the reduced state. So for this half cell reaction, what will be the form of the Nernst equation? So it will be E half cell equal to E0 half cell minus of 0.05912 by n log what is the product here is the reduced state. So log of concentration of the reduced state and the concentration of the oxidized state. So in this way or by using this equation, we can simply calculate the half cell potential for a half cell reaction. So let us discuss a very important topic, the relation between the free energy and EMF of a cell. So during the operation of a cell, the decrease in gas free energy or free energy appears as the electrical energy. So this can be represented using the mathematical equation minus of delta G equal to NF E cell. So where delta G is the change in gas free energy or simply free energy of the process or the reaction, and n is the small n is the number of electrons transferred during the process, and F is the Faraday's constant, which has a value of 96,500 coulomb per mole, and the E cell is the cell potential. So from the concept of spontaneity, we know that for a process or reaction, for a chemical process or a reaction to be spontaneous, delta G must be negative. So if we look at this equation very carefully, we can find out that here N is a positive quantity, which is the number of electron transferred, which must be positive. F is a constant, so it is also a positive quantity. So the quantity, the sign of delta G will solely depend on the sign of the cell potential, that is E cell. So for a cell to be cell reaction, working condition of a cell reaction to be spontaneous, the value of delta G must be negative. So in that case, E cell has to be positive for the cell to be for the cell or cell reaction to be spontaneous. Or in the other hand, if either of delta G is positive or E cell is negative, then the working condition of the cell will be simply non-spontaneous. Now, let us discuss the various application of this Nernst equation. So the most important application of the Nernst equation is that we can predict the electrode as well as the overall cell potential of any cell reaction at any arbitrary ion concentration. So let us discuss this with the help of a problem. So let's say we want to find out the potential of the following half cell. So FeSO4 with concentration 0.1 molar to which is converting to Fe solid at 298 Kelvin, and the standard electrode potential of this half cell is minus of 0.44 electron volt. So in the ionic form, if we write the half cell reaction, it will be Fe2 plus aqueous plus 2 electron to Fe solid. Now if we apply the Nernst equation for this half cell reaction, it will be simply E equal to E, that is E cell equal to E0 cell, or E0 simply minus of 0.05912 by N log of concentration of the reduced state divided by concentration of the oxidized state. So here the reduced state is the Fe solid and the oxidized state is Fe2 plus. So since Fe concentration of Fe solid is 1, this equation will simplify it to be this one. Now if we put the value of E0 cell and also the concentration of Fe2 plus to be 0.1 molar, we will get the value of E cell, or simply E, to be minus of 0.4695 volt. Another application of Nernst equation is that we can evaluate the equilibrium constant from this Nernst equation. So the simplified form of the Nernst equation I have written here is the E cell equal to E0 cell minus of 2.303 RT by NF log of Q. So this is the generalized form, since we are not assuming T to be 298 Kelvin, where Q is the reaction quotient, that is the concentration of the product divided by concentration of the reactant. Now, what is the condition of equilibrium? From the free energy and EMF relation, we know that when E cell will be 0, delta G will be 0, and that is the condition for equilibrium, and in that case we can say that Q will become the equilibrium constant K. So if we put the values of E cell to be 0, the equation becomes E0 minus of 2.303 RT by NF log of K equal to 0. Now from this equation, log of K will be NF E0 divided by 2.303 RT. Now again, if we assume that the temperature in the Kelvin scale to be 298 Kelvin, and if we put the values of Faraday's constant, universal gas constant, the equation will be log of K equal to NE0 divided by 0.05912. So from this equation, the value of equilibrium constant will be K equal to 10 to the power Ne0 divided by 0.05912. So simply by putting the value of E0 and the number of electrons chain for a particular reaction, we can calculate the equilibrium constant for that reaction. Let us discuss a problem regarding calculation of equilibrium constant. Say for example, we want to calculate the equilibrium constant for this cell reaction where the standard reduction potential for the half cells are 0.77 and 0.54 volt. So first we will calculate the standard cell potential for the given reaction, which will be 0.23 volt. Now, using the previous equation we have shown, we can simply put the value of E0 and number of electrons change for this reaction, and we will get the value of equilibrium constant for this particular reaction. Now, let us discuss the another use of this Nernst equation, which is the pH measurement and ion selective electrodes. So, the operation of a pH meter, which we use in laboratories, is relies directly on the Nernst equation. So, a glass pH electrode measures the potential difference between a reference solution and the test solution. So, as the potential varies linearly with the concentration of hydrogen ions, which is designated as concentration of H plus within third bracket, the measured voltage can directly be converted to a pH reading by simply using this equation. So E cell equal to E0 cell minus of 0.0592 into pH. So from this equation, if we know the value of E cell and E0 cell, we can simply calculate the value of pH of that particular solution. So by using similar principle, uh, we we may apply to other ion selective electrodes, which are used to measure concentration of specific ions like F minus, Na plus, or Cl minus in laboratories and different water treatment facilities. So, what are the advantages of this Nernst equation? The first one is that we can predict the cell potential accurately under non-standard condition. So what is this non-standard condition? It means that we can calculate the cell potential of any cell reaction with or any half cell reaction at any temperature or any concentration of the reactant or product. It is applicable to a wide variety of electrochemical cells, and it links electrochemistry with thermodynamics and chemical equilibrium. We have already discussed it, and it also forms the basis of many analytical instruments. So now, what are the limitations? So the first one is that it assumes ideal solution behavior, that is, in most of the cases we approximate activities to be concentration. So the second one is that accuracy decreases at high ionic strength. When the ionic strength is very high, accuracy will decrease. This equation is best suited for system which are at equilibrium or near equilibrium condition, and the temperature variation requires adjustment of this Nernst equation. So thank you very much for listening to me.